Qualitative Analysis from October-November 2015, variant 3.1. In this question, they have said, at every stage of any test, you are to record the details of following: any color change seen, formation of any precipitates, solubility of such precipitates in excess of reagent added, and then where the gases are released, they should be identified by a test described in the appropriate place in your observation. Then you are to indicate clearly at what stage in a test a change occurs. Then no additional tests for ions present should be attempted. If any solution is warmed, a boiling tube must be used. Rinse and reuse the test tubes and boiling tubes where possible. So this is the basic information in every paper they say. Now, the question starts from here. Fa6 is a sodium compound containing one anion listed on page 11. Dissolve Fa6 provided in about 15 centimeter of distilled water in a boiling tube. Carry out the following test and record your observations in the table. Now, here we have two tests to perform. So let's prepare this solution first. Fa6 in 15 centimeter cube distilled water in a boiling tube. Now I will take given Fa6 in a boiling tube and I will add 15 centimeter cube of distilled water. So for that I will use measuring cylinder. I will take 15 centimeter cube of distilled water in this measuring cylinder. Now it's approximately 15 centimeter cube here. Now I will add this and this in a tilted tube so that it will dissolve completely. Now we can see the solid is completely dissolved. So this is my Fa6 solution prepared. In the next part, they have said to a 1 centimeter depth of the solution of Fa6 in a test tube, add a few drops of barium chloride or barium nitrate, then, and there is a dotted line in between, it means in the same test tube, add dilute hydrochloric acid. So let's perform this test. Now, in the 1 centimeter depth of solution of Fa6 prepared, this is 1 centimeter depth of solution Fa6, and now we will add few drops of barium chloride. So as soon as we add few drops of barium chloride, white precipitates are formed. Now, if we add hydrochloric acid, I am adding with a dropper hydrochloric acid, and if I add hydrochloric acid using dropper, these precipitates are partially dissolving, and if we add a bit more, these precipitates are partially dissolving. So the color you can see is getting lighter, and if I add a bit extra, so now those precipitates are dissolving. It means when barium chloride is added, precipitates are formed. It means sulfate or sulfite is present, and if we add acid and those precipitates dissolve, it means sulfite is confirmed. So we will record this observation. So when we have added barium chloride, white precipitates formed, and if we have added hydrochloric acid there, white precipitate dissolved. In the table of anion, we can see for sulfate and sulfite, we add barium nitrate, which gives white precipitates in both of them. But if we add dilute acid, those precipitates show variation either by dissolving, it means soluble, or insoluble. In our case, the precipitates were soluble, it means sulfite is confirmed. Now, let's move on to the next part of this question, which says to a 1 centimeter depth of the solution of Fa6 in a test tube, add an equal volume of hydrogen peroxide, which is an oxidizing agent, and of course it will oxidize your sulfite in the given compound. And then in the same test tube, means dotted line, in the same test tube, add a few drops of barium chloride or barium nitrate, then again in the same test tube, hydrochloric acid. It means if you have found sulfite here in the first part, you are adding hydrogen peroxide so that sulfite will oxidize and it will form sulfate. And then again you are testing sulfate by dissolving it in barium chloride followed by hydrochloric acid. So let's perform this test now. Now I will take in another tube 1 centimeter depth of the solution prepared, Fa6, 1 centimeter depth. And now I will add hydrogen peroxide So as soon as I have added hydrogen peroxide, here we can see no visible change appeared. Now let's add barium chloride, few drops. As soon as we have added barium chloride, we can see white precipitates start forming. And now, if in the same test tube I add hydrochloric acid to confirm sulfate or sulfite, so those precipitates are not dissolving. It means sulfite are oxidized to sulfate. Now we will record this observation. So we have recorded all this information here, and now we can see again, after adding barium chloride or barium nitrate, if white precipitates are formed and they become insoluble in acid, it means sulfate is confirmed. From here we can conclude that in our Fa6, which was a sodium compound, basically the anion was sulfite. In this test it is confirmed, and now we have confirmed it again by adding hydrogen peroxide so that it is oxidized and forming sulfate, and white precipitates of sulfate, barium sulfate, remain insoluble in acid, means the Fa6 was sodium nitrite. Now let's move on to the next part of this question, in which they say to a 1 centimeter depth of the solution of Fa6 in a boiling tube, add an equal volume of Fa2, which is sulfuric acid, then heat the mixture gently and cautiously, because you are heating a solution that contains acid, so you must take care while heating, not direct flame, too much of heat should be given. So let's perform this test now. We will take in a boiling tube, which is a bit thick tube from the normal. You can see this is thick a tube made of Pyrex for heating purpose. We will take 1 centimeter depth of our Fa6 solution, in this boiling tube. And now we will add equal volume of sulfuric acid. As soon as we add equal volume of sulfuric acid, we can see there is no visible change happening. But if we realize we have added sulfuric acid in sodium sulfite, it means a mixture of sodium sulfite and sulfate is produced. Now they have said heat or warm this gently. It means when sodium sulfate and sulfite, which is present in the solution, are heated, sulfur dioxide will be produced. Now if we want to test the gas liberated, because every time when we have any gas liberated, we have to test and identify that gas. It means if sulfur dioxide is going to be tested, sulfur dioxide is a reducing agent as well as it is a bleaching agent. So to test the presence of reducing agent, we can use potassium permanganate. Potassium permanganate, and potassium permanganate gets reduced and decolorized. So now how to test a gas using this liquid potassium manganate? What we do is we normally take a filter paper, and in the filter paper we dip this in potassium manganate so that the solution turns this white paper purple. As soon as the gas will be liberated, we will put this at the top here, and we will see the exposed part should be from purple, should be decolorized. So let's warm this mixture. Let me warm the solution produced. We will put the test tube holder there, and now we will put our potassium manganate dipped paper. We will take this filter paper and we will make it damp by using this purple solution, which is potassium manganate. We will put this here. Now you can see this is purple, and now we will add this here on the top of this test tube. So it's here now. The exposed part is here, which is a bit purple. Now let me switch on the burner. Put the chemicals aside while you are heating anything. Now let me warm this a bit. So now we can see the exposed part is totally colorless, white, and we can see also the remaining part is brown in color. So exposed part means decolorized, means sulfur dioxide has bleached this part. So sulfur dioxide is confirmed. So let's record this observation. So I have recorded this observation. And then let's move on to the next part, where they say to a 1 centimeter depth of the solution of Fa6 in a test tube, add equal volume of sodium hydroxide, then add a few drops of Fa1, which is aqueous potassium manganate 7, and in the same test tube then add sulfuric acid. So let's perform this test now. Now we will take 1 centimeter depth of Fa6 solution, and we add equal volume of aqueous sodium hydroxide. As soon as we add aqueous sodium hydroxide equal volume, we can see no visible change is coming up. Now let's add potassium magnate, and if we add few drops of potassium magnate, we can see a green solution is produced. So the color changed to green. Now we will add sulfuric acid. So again, the solution turned colorless. So we will record this observation now. So we have recorded this observation here. Let's move on to the next part of the question, where they say, identify the anion in Fa6 and state one piece of evidence from your identification. So we can conclude that this solid has sulfite as an anion present. And how can we conclude? Because of two evidences from here. If we go back in this part, we can see when we have added barium nitrate, white precipitates were formed which were dissolved in hydrochloric acid. This is one piece of evidence. And then here also we can see that if we have added sulfuric acid and gently warm, a gas is given off which is tested by aqueous KMnO4 on a paper, and that has turned colorless. So these are the two evidences. We can write any one of them here. So let me write here. So I have recorded the information here. Now let's proceed on to the next part, where they say give the chemical equation for the reaction of Fa6 and hydrogen peroxide in test 2. State symbols are not required. Now in part 2, what we have done, in part 2 we have added hydrogen peroxide in Fa6. Now in this case, Fa6 was actually a sodium compound and the anion confirmed was sulfite. It means sodium sulfite. So if it is a sodium sulfite and we have added hydrogen peroxide, which is an oxidizing agent, so it will oxidize sulfite to sulfate. So sodium sulfate will form along with water. So let me write the equation now. So I have written the equation here, and if anyone is confused with how to write the formula of sodium sulfite, we know that sodium is a group 1 metal, so it has a +1 charge. And if we want to see the charge of the sulfite, SO3 has a -2 charge. So once we write the formula, we just cross the charges. So Na2SO3 is the formula, and again for Na2SO4 for sodium sulfate. So let's proceed on to the next part of this question. Now in this part they say Fa7, 8, 9 and 10 each contain cation, one cation from the list on page 10. You will attempt and identify the cations by testing with sodium hydroxide and aqueous ammonia and complete this table. In each case, you use a 1 centimeter depth solution in a test tube. Now we can see we have been provided with 4 of these solutions, and we are looking for the cations by using sodium hydroxide and aqueous ammonia. So let's perform these tests one by one now. Now let's take 1 centimeter depth of Fa7 and add few drops of aqueous sodium hydroxide first. So if we add a few drops first, white precipitates are formed, and if we add in excess, those white precipitates are not dissolving. Now let's move on to the Fa8 in a test tube, 1 centimeter depth of Fa8. And again, we add few drops of sodium hydroxide first, and we see white precipitates are forming. And if we add an excess, those white precipitates are not dissolving. Let's move on to the next chemical, that is Anion. We take 1 centimeter depth of Fa9 and we add few drops of sodium hydroxide, and we can see white precipitates are forming. And if we add sodium hydroxide in excess, we can see the precipitates are dissolving. Confirm by adding more. So they are dissolving. Now let's move on to the next Fa10, 1 centimeter depth of Fa10, and add sodium hydroxide first. So white precipitates start forming, and precipitates are gradually turning brown. So precipitates turned into a light brown color. And if we add an excess, those precipitates are insoluble. So let's record all these observations now. Now we will take 1 centimeter depth of Fa7, and now we will start testing it with aqueous ammonia. So once we add few drops of aqueous ammonia, we can see no change is appearing. If we even add in excess, no change, no precipitates. Now let's move on to the Fa8, 1 centimeter depth. Again, few drops followed by excess. So as soon as we add few drops, white precipitates start appearing, and if we add in excess, those white precipitates are not dissolving. Now take 1 centimeter depth of Fa9 and the same aqueous ammonia. Few drops first. White precipitates start forming, and if we add an excess, those white precipitates are not dissolving. Let's move on to the last one, Fa10, 1 centimeter depth. Again, aqueous ammonia, few drops. So as soon as we add few drops, white precipitates which are turning brown, and those brown precipitates are, those white precipitates turning brown remain insoluble in excess. So let's record all these observations. So I have recorded all these observations here. Let's move on to the next part, which says, from your observations, identify as far as possible the cations present. Now, if we look at Fa7, it has given white precipitates with sodium hydroxide and no change, no precipitate with aqueous ammonia. And if we look here in the table, barium 2 plus and calcium shows these responses. It means this Fa7 is either barium 2 plus or calcium 2 plus. So let's write this here. Now let's move on to the next one, which is Fa8, which has given white precipitates with both of the reagents, and the precipitates were insoluble in excess. And if we look here, out of all these observations, only magnesium has shown white precipitates which were insoluble in both the reagents. It means our Fa8 has magnesium 2 plus. Now Fa9 has given white precipitate which were dissolved with sodium hydroxide. So if we look here, aluminum 3 plus white precipitate soluble and zinc 2 plus white precipitate soluble. So we are confused with aluminum or zinc. Now let me proceed with the aqueous ammonia, which has shown white precipitate insoluble in excess. Now here white precipitate of zinc are soluble with ammonia, and aluminum has got white precipitate insoluble with ammonia. It means from here we can conclude Fa9 has aluminum 3 plus. Now Fa10 has white precipitate that were turning rapidly brown and insoluble in excess with both. So here we have only one Mn2 plus that gives this type of response of white precipitate turning brown in air and insoluble in excess with both of them. So Fa10 has Mn2 plus. So let's record this also. So we have recorded all these observations and conclusion here. Let's move on to the next part where it says, give ionic equation for the reaction of one of the cation with sodium hydroxide. So whenever we write the ionic equation with sodium hydroxide, we write this way, that magnesium 2 plus with hydroxide, any metal whose charge whatever it is, we add that many hydroxide ions and we form precipitates of its hydroxides. So here we have magnesium hydroxide formed as precipitate. In this case you can see insoluble precipitate in Fa8, right? So we write ionic equation this way. Now let's proceed with the next part where it says the precipitates obtained when alkalis are added to the solutions of certain cations are sometimes difficult to see. Suggest how using no additional apparatus, the experiment could be repeated in a way that would make these precipitates more visible. So sometimes if we are not getting precipitate, it means we are adding chemical that has a very low concentration. So in order to obtain better results, we can increase the concentration of our chemicals like sodium hydroxide and aqueous ammonia for the test of cation where we add these two chemicals. We can increase the concentration of these two so that the results will be more evident and more profound. So we have written here, use high concentration of alkali. Here we comes to an end of 16 mark qualitative analysis question.